Hello, it's Dr. Daystorms, and in this section, Chapter 7, we're going to be discussing two important yet related aspects of ion formation. The first is ionization energy, and the second will be electron affinity. Ionization energy is just the amount of energy it takes to remove an electron from the ground state of the gaseous atom or ion. So what that means is just a fancy way of saying is how much energy does it take to remove one electron. Okay? And so because of that, the very first electron that you remove is called the first ionization energy. If you remove a second electron, it's called the second ionization energy. The third would be the third ionization energy, so on and so forth. However, if we just look, remember we are looking primarily at those electrons that are in the outermost energy shell, which are called valence electrons. Okay, so that's the outermost orbital, like the n equals whatever orbital. So now let's just look at the trends that you can see in ionization energies. This should make sense. It always takes more energy to remove the second electron than it does the first. You don't have to take as much energy to remove a first electron. It takes more for the second, more for the third, fourth, fifth, sixth, seventh, and eighth. Okay, and that's what this table here is depicting. What happens is whenever all the valence electrons have been removed, it takes a huge amount of ionization energy to take the next electron. So let's see what I mean here. Remember, sodium is in the first column of the periodic table, so it only has one valence electron. It takes 495 joules to remove this electron, but once you do remove it, it looks just like neon, which is a noble gas. So sodium then will have 10 electrons. It's got 11 protons. That's why it's now sodium plus cation, because it's got 10 electrons in it. It looks like neon. It likes to look like neon. It likes to have that noble gas configuration. It's happy. If you try to remove the next electron out of it, see, it goes up from 495 joules to 4,562. It's a huge leap because it's happy when it looks like a noble gas. If we look at magnesium, which is in the second periodic table, the second column on the periodic table, so it has 2 electrons in its valence shell. It takes a little bit more energy to remove that first one than sodium. It takes a little more energy to remove the second one, but then it's happy because it too looks like neon. So you go to remove that third one, and it takes a lot of energy. This is true for all of the atoms. And if you notice, if we look all the way at argon, which is the noble gas on that row, it takes a lot of energy just to remove any electrons from it because it's perfectly happy. This is a cartoon way of showing in 3 dimensions the trends in ionization energy. As one goes down the column, it takes less and less energy to remove an electron, which makes sense because even though they're all in the same family or group, the Z effective is essentially the same. However, the valence electrons get further and further and further away from the nucleus. Remember, the nucleus has the protons that help holding the electrons in place. And so, therefore, you get down here to cesium or francium, and it doesn't take hardly any energy to remove that first electron. Because it's so far away. It's in the 6th row. So, therefore, there's going to be n equals 6. So it's really quite simple to remove that first electron. As you go across the same row, you see that it gets harder and harder to remove an electron, because as you go from left to right, the Z effective increases. However, that being said, I'm hoping that you can see there where this is the first row hydrogen and helium. This is the second row from lithium to neon, the third row from sodium to argon, potassium to krypton, so on and so forth. Hopefully you see that there are a couple of exceptions or a couple of anomalies in that trend. It's not perfectly increasing. Okay? So there are two apparent discontinuities in this trend. So let's explain the reasons why the energy actually decreases between the group 2A and 3A and the group 5 and 6A. So the first occurs between groups 2A and 3A. Why is that? So let's think about what these look like. I'm just going to do an example. We've got, let's do, let me redo this. Let's think about this. If it's group 2A, that means it's going to have 2 electrons in its outermost energy shell. So those are both in the s orbital. So for example, let's just say that this is 2s2. Okay? So what is group 2s2 is beryllium. Whereas if it was group 3a, which is boron, it's going to have 3 electrons in its valence. So it's going to be 2s2, 2p1. So the s orbitals are completely full, but you just have 1 lone electron in the p orbitals. That's the reason why, since it doesn't have any other electrons around it, it's actually more easy to remove this electron than it is to break up a full s orbital. So the electron removed from the p orbital rather than the s orbital is further from the nucleus, and there's a small amount of repulsion by the s electrons. Now let's try to explain the next anomaly. This happens from groups 5A and between groups 5A and 6A. So let's just draw examples of 5A and 6A. So if it's group 5A, it means there are 5 electrons in the outermost shell. So here's the 2s. I'm just going to do ones from the second row of the periodic table. So it's going to be 1, 2, 3, 4, 5. Whereas if it's group 6A, it's going to be 1, 2, and the 2s. In the 2p, there's 1, 2, 3, 4. So it's actually easier to remove 1 electron from this doubly occupied orbital because there is repulsion between those 2 electrons. They're not perfectly happy. So because of that, it's a little easier to remove it than it is to remove just one of these. So it just goes, oh, whoops, I forgot to put that this was 6A. It goes and it just loses the 1 electron that I'm going to highlight here. That electron will disappear, and now you've got a cation. So the electron that's removed comes from a doubly occupied orbital, and the repulsion from the other electron makes it a little easier for it to help in its removal. So that's ionization energy. That's whenever you're trying to remove an electron. What about whenever the energy that accompanies whenever you try to add an electron? So now we're going to make anions before we were talking about making cations, now we're making anions. So the example here is, for example, chlorine becoming the chloride anion. So remember, chlorine has 7 electrons in its outermost shell. It adds one more, it's got 8, and so therefore it looks like a noble gas and it's happy. So if you just look here, in general, if you look at the trends, usually as we go, if you just look at the lithium versus fluorine, as you go across the periodic table from left to right, it becomes more and more exothermic. It becomes easier or even more or better to actually add an electron. Once again, though, there are 2 exceptions. We have the exception here between group 1A and 2A, and then we have the exception here again between 4 and 5A, to where you are trying to add electrons. So let's explain that. Why is it that between 1A and 2A, the added electron has to go into a p orbital, not the s orbital? So because of that, the electron is further from the nucleus. It's going to feel the repulsion from the s electrons and less pull from the positive charged nucleus. So that explains the whole idea that it's easier to actually add an electron to lithium than it is to add the electron to beryllium, because beryllium would have to go brand new into the p orbital, so it's got to go past the s orbital and get into that p orbital. Likewise, the second one happens between groups 4 and 5A. This one's really actually quite simple, because group 5A has no empty orbitals, so the extra electron has to go into a p orbital that already has an electron in it. So what do I mean by that? So, group 5 means it's going to have 5 electrons. 1, 2, 3, 4, 5. Now for electron affinity, that's any energy that you get out by adding another electron. It would have to go in this orbital here, and that orbital already has an electron in it, so there's repulsion there, so it makes it more difficult than what you would expect to add it in there, since it's going to be the first one to make a doubly occupied orbital. Hopefully this has helped explain a little bit about ionization energy and electron affinity. Just remember, ionization energy is the amount of energy it takes in order to remove an electron. Electron affinity is the amount of energy that's given off by when you add an electron to make an anion. I'll see you in class.